Okay, so we briefly discussed a multi-particle system yesterday. So we defined something called as, free settling, okay, and something called as hindered settling, right? And we said that hindered settling is going to occur if you have cases where the particles are close enough, okay, or if there's a kind of a coupling of the way the particle settles, okay, with the wall of the container or with other particles in the system, okay, then that's when we call what is called as a hindered settling, where the motion of the particle is kind of influenced by the other particles in the system plus the wall of the container, right? And we said that so basically people have kind of proposed some empirical equations of this sort, that is the settling velocity under hindered settling condition, okay, goes as this is a free settling velocity multiplied by some term which depends on epsilon, which is the volume fraction of the liquid that you have in the slurry or the suspension, and n is an exponent that takes different values depending upon what kind of fluid particle system that you're working with, okay. And we said that if you take Stokes law regime, then n is going to be of the order of 4.6, and if you take the Newton's settling regime, your n is going to be of the order of 2.5, right? That's what we said. And then we just wanted to set this problem up, and I said that if you really want to look at the settling velocity in the multiple particle system, I mentioned that you can actually start with assume a particular settling regime, either Stokes or Newton's, okay, and then you basically write down whatever is the working equation for settling for each of these cases. So we just took g dp square into rho p minus rho divided by 18 mu. You take that and you modify it to suit the multi-particle system, right? That's what we mentioned, and in that connection we said you're going to make two modifications, okay. Modification one is that your rho, which is the density of the fluid, is now you would have to worry about replacing that with the density of the suspension or the slurry, right? And we said that basically goes as rho of particle into 1 minus epsilon, where epsilon 1 minus epsilon basically gives you the fraction of the solid that you have in the system, plus rho of the fluid multiplied by epsilon, right? That's one modification. And the second modification that we said is you should replace your mu, okay, with some sort of effective viscosity, okay. And we said this mu effective, okay, mu effective is going to be something like mu divided by f of epsilon, okay. And we said that this function f of epsilon is typically less than 1, that is because we have seen examples where we know that the viscosity of a fluid with the particles present is higher than the viscosity of the neat fluid itself, right? And I was trying to answer a question yesterday wherein we said that if you have, like, say, a liquid flowing through a container, right, through a pipe for example, and if you say that there is some sort of there's a you can think about them as streamlines for example, right? Now what will happen is, if you have a similar case with the particles, okay, what happens, the presence of the particle, it basically obstructs the fluid flow, right? And in that sense, your liquid is going to be stopped, okay. So now the fact that there's a slowing down of the liquid, so your average velocity gradient, okay, basically reduces, okay. And if you have this mu tau is mu times dv by dy, the fact that the average velocity gradient goes down when you have the particle, for compensating that your viscosity has to go up, okay. This is one way of thinking why does the viscosity of the fluid increases if you have particles in the system, okay. So therefore your f of epsilon is a function which is less than 1, okay. That you would have to come up with a way of working around it, right? And I also mentioned that in the case of multi-particle system, your relative velocity, right, is typically related by, that's the relative terminal velocity. That's because of the fact that you have, in the case of a single particle system, your fluid was stationary, your u of the fluid is essentially 0, right? Only thing that was settling was the only thing that was moving was the particle, right? But if you have a multi-particle system, as the fluid is displaced, the fluid is going to go up. Okay, there's going to be a UF component as well, and this UF is actually U of particle minus U of the fluid, right? That's how it is. And then and we just derived that it basically goes as UT, which is the terminal settling velocity under the free settling conditions, multiplied by epsilon into f of epsilon, right? If you go back to this expression, substitute for rho in terms of rho suspension, right? And then replace mu with mu effective. So that's what you will end up with. Okay, your U relative terminal is going to be settling velocity under free settling conditions multiplied by epsilon times f of epsilon. Okay. Now, so before we go on, go further, I just want to introduce a few terms. Okay, typically when people do multiple particle settling, right? Typically people carry out certain type of experiment, which are what are called as a batch settling experiments. Okay, in batch settling, what basically happens is you have a container, and that container is basically filled with particles. Okay, and basically you watch this container with the fluid particle system as a function of time. Okay, that's what is typically done. Okay, now if we define a couple of quantities, something called as a QP, okay, something called as QP, where QP is the volumetric flow rate of the solid particles in the system. Okay, the particles are coming down, okay, or settling, right? And there is some velocity associated with the way the particles move in the fluid, right? Okay, based on the velocity, and if there is an area that is available for them to settle down, right? So your QP is what is called a volumetric flow rate, right? And that would depend on some velocity, right? And P stands for the particles, right? I'm going to use a subscript F, okay? Subscript S, okay? And this S is what is called a superficial. It basically stands for superficial times A, where A is the cross-sectional area that is available for the particle to settle, right? So if you have a container, if you have a cylindrical container, your cross-sectional area is going to be, your whatever circle area, right? Now, so if you define, okay, if you define the velocity, okay, that is associated with the particles by considering A, which is the entire cross-sectional area of the container, okay, then this velocity that you have it here, it is what is called as a superficial particle velocity. Okay. Similarly, if I define volumetric flow rate for the fluid, that is QF, okay, and if I say that the velocity with which the fluid is basically moving is again F for fluid and S for superficial. Again, if I use the entire cross-sectional area of the container, that's when these velocities are what are called as a superficial velocities. But however, we know that out of this entire cross section, certain area is occupied by the particle and certain area is occupied by the fluid, right? Therefore, if I actually consider the actual area that is available for the respective fluid and the particle, okay, then you define what is called as actual velocities, okay, which basically is, if you say that your QP, okay, is U particle superficial times A, okay, is equal to U of just the particle times what is the area that is available for the particle to settle, is going to be, what is that? So if you have a container, right, okay, say that the cross section area is A, right, and if I say that if I want to have an idea about what is the cross sectional area that is available for the particles to flow, it is A into 1 minus epsilon, right? Because if I say that the 1 minus epsilon gives you the solid fraction, right? The only thing that I am assuming here is volume fraction is typically is a 3D quantity, right? It's basically for the entire fluid particle system. If I assume that the area fraction, okay, is equal to the in a 2D sense, okay, what is the fractional area that is available for the particle to settle is this, right? Is that okay, or do you have some? Now similarly for the fluid, okay, it's U fluid superficial times A, and that should be equal to U of F into A times epsilon, right? Because epsilon is the liquid fraction, right? So therefore, in any fluid particle system, if you are basically considering the entire cross sectional area that is available, okay, in the calculation of your velocities, that is what is called as a superficial velocity. But if you only consider the respective area that is available for either the particle or the fluid into consideration for getting the velocity of the fluid or the particle, these are what are called as actual velocities. In this case, these are the actual velocities, and these two terms are what are called as a super. Is that okay, or any doubts? Yeah, it's just a convention that people use. That's about it. Okay, whether you because we know that the way to go from the volumetric flow rate to the velocities, you would have to divide that by the area, right? Cross section area that is available for the flow. Okay, if I take the entire cross section area that is available both for the particles and the fluid put together, that is what is called as a superficial velocity. However, if I separate out the fractional area that is available for the particle and the fluid, okay, if I use only respective area available for each of these species, then it's what is called as a actual velocity. That's the convention. Okay. Now, so now when you do a batch settling experiment, okay, because the way as I said, right, the way the batch settling experiments are done is you basically take a container, right, fill in your particles and the fluid, right, and you just watch as the settling occurs, right. So in such a case, if I can write that because of the fact that I'm not adding any fluid or the particle into the system externally, I can say that your QP plus QF should be equal to 0, because in a sense there is no net flow. Okay, therefore your the volumetric flow rate of the particles plus the volumetric flow rate because of the fluid, that should be equal to 0, right, because there is no net flow as such. I'm not adding anything to the system, or I'm not taking anything out. Okay, so now therefore I can write QP. So now I can define QP in terms of your actual velocities, right. QP I can write it as UP times A times 1 minus epsilon, okay, plus UF times A times epsilon should be equal to 0. Okay, therefore I can just cancel this throughout. Therefore your UF becomes minus of UP into 1 minus epsilon divided by epsilon, right. Is that okay? Now with this, what I can do is I'm going to use this and then go back to the equation that we developed, okay, which was UT U relative T, right. U relative T was UT times epsilon times F of epsilon, right. We had this expression, right. So I'm going to substitute this back here. Okay, so what are we going to do? What I'm going to do is I'm going to write it as UP minus UF, right. That's I said U relative T is going to be your UP minus UF, right. That's what I said, because because both the things are moving here. Okay, should be equal to epsilon square into F of epsilon, right. Now I know that if you go back this expression, right, I can substitute for UF in terms of UP, right. Is that okay? So I go here. So this is UP plus UP into 1 minus epsilon divided by epsilon is going to equal to, I'm sorry about that, that's going to be this is not correct, no? It's just epsilon, right? Okay, that should be equal to your epsilon into f of epsilon, right? So if I simplify this, I basically get up, okay, terminal, okay, I'll say terminal is going to be equal to epsilon square into f of epsilon, right? That's what you get, right? Because there's an I can take up out, so epsilon gets cancelled. 1 over epsilon is what you have here. Basically, that's what I end up with. Is it okay? What is that? On the right hand side? No, because see, UF, I'm basically replacing UF in terms of UP into 1 minus epsilon divided by epsilon, right? Okay, that's what I've done here. Oh yeah, sorry, so there's UT here. I'm sorry about that, right? That is your, free settling velocity, right? Or the settling velocity under free settling conditions, right? Now, if I want to, now I still don't know what is f of epsilon, right? Because if I want to go back and think about the plot that we saw, right? You had n, which was a function of Reynolds number, right? So if I want to get that n, I still need to find out what is this f of epsilon, right? So what people have done is there are a lot of theories available for what this f of epsilon is. Okay, people have done a lot of theory, as well as there are a lot of experiments available, wherein we know something about how the viscosity of the fluid changes as a function of particle concentration. Okay, I'm just going to put up some result from the literature. So this is a plot. The line that you see is a line for this expression that you have on the on the slide. Here eta is the viscosity of the particle filled system, okay, or is the viscosity of the slurry or the suspension, and eta naught is the viscosity of the pure fluid without any particles, okay, the suspending medium, and f is the volume fraction, and this line is actually the fit to this equation, and the data point that you see here is the experimental data, okay, right? And this is one of the theory that is developed by Einstein, okay, and so therefore what I can do is in terms of the effective viscosity function, okay. Now if I write this as eta is going to be eta naught into 1 minus phi into, right, minus 2.5, okay, and we know that the viscosity of the particle fluid system is actually greater than, is larger, right? So therefore your f of epsilon, okay, the function that we want, it should actually be 1 over 1 minus phi into minus 2.5, right? That's your f of epsilon, okay. So what these relations, which basically correlate the viscosity of the particle filled system to the viscosity of the neat system and the volume fraction, what they will give you is they will tell you a way of actually getting this, the f of f function, which is what I need for me to go back and kind of complete my derivation of finding out what the settling velocities are, right? Let me just go back to right here. So what I can do is I can write this as ut into epsilon square, right, into 1 divided by 1 minus phi to the power of minus 2.5, right. I can write this as ut into epsilon square into 1 divided by 1 minus phi is your epsilon, right, that's the liquid fraction, to the power of minus 2.5. So therefore your ut basically becomes 4.5, right. Your ut is up relative, okay, that is the particle term in. So this up stands for the particles, right, that's the terminal velocity of the particle which is settling in a multi-particle system, okay, where the hindered settling becomes important, basically goes as the free settling velocity multiplied by your epsilon to the power of 4.5, and of course there are some conditions under which this is applicable, okay. Typically this is typically used where the concentration of your particles is up to about 10%, okay, or 0.1, okay, but of course depending upon the epsilon that you're looking at, the liquid fraction or the phi that you're looking at, depending upon the Reynolds number of the particle that you're working with, okay, you will have different functional form for f of epsilon. You would have to use appropriate functional form and then substitute in an equation like this, okay. And as we said, right, this is only applicable if I am working with the particles of smaller size, where the Reynolds number comes into the Stokes settling regime, right, because we started off with the Stokes settling regime, right. However, if you want to work with other settling regimes, you would have to appropriately modify the expressions properly. Yeah. Okay. So therefore, basically the idea of talking about this, it kind of tells you something about how do people think about multi-particle system. And then yeah, go ahead. That's because see these okay, all these expressions that we developed, right, the Newton's regime, the Stokes regime, everything, typically this is applicable for cases where you have a stagnant fluid, okay, and say that you let a particle into motion either by inducing gravity, or right, in that sense your fluid is still stationary, okay, there is no net flow of the fluid as such, okay. Though this is ut, it should actually be ut minus u of fluid, okay. This is for the particle and this is for the fluid, but the fact that the fluid is stationary, it basically turns out to be the terminus of the particle itself. Yeah, epsilon should be, yeah, I mean, as I said, right, people have kind of developed like for example, so this is typically valid for about 10%, but what is that? Dilute systems, yes, yes. No, so it turns out that the f of the functional form that you have, okay, people have different functional form. For example, if you go for concentrations which is typically up to about say 0.03, that is 3% by volume, okay, this f of epsilon is typically 1 divided by 1 plus 2.5 times phi, okay, which is basically a special case of this, right. If I take this and then if I expand it into higher order terms, like if I neglect the higher order terms, basically I recover this, right. So therefore, the f of epsilon that you choose, it depends on the kind of concentration that you're working with, so in that sense, so you would have to choose appropriate values of f of epsilon. Yeah. Okay, any more questions? No. So so what I'm going to do is okay, so I'm going to talk a little bit about in experimentally what people do is this, okay, when people are given a slurry, okay, and you want to find out their settling behavior, people do what is called as a batch sedimentation test, okay, it's called a batch settling test or a batch sedimentation test. These experiments are as simple as you take a container, fill your slurry and just watch the container as a function of time, okay. So what you see are the images at 3 different instants of time, okay, time t1, t2, t3 if you want to call it as, right, or say t0 to begin with and some other time t1, t2. And what happens, what you look at in the case of picture corresponding to T0, you have a slurry which is a uniform slurry. The concentration of the slurry, as a function of height is exactly same. That means no matter from which pocket of the container I draw the solution, I measure their volume fraction is exactly same. Okay, it's a uniform slurry, and correspondingly, if you look at the concentration plot, the concentration everywhere throughout the height is Cb. That's the concentration of the particle that you start with, okay, and it is uniform throughout the height, okay. Now with time, what you would see is you get in the container, you'll start seeing different zones that are formed, okay. There could be a case where you have a zone with clear liquid, that means there are no particles in the system, all the particles in that upper layer have come down, okay. And you have a zone B where the concentration of the particles in the zone, in the second zone is exactly same as the concentration of the particle that you started off with, okay. And then of course at the bottom you have something called as a S, that's a sediment, okay, and where the particle concentration is going to be very high, right. So therefore, if you were to look at the particle, the concentration as a function of height, the concentration is 0 there because there are no particles, it's a pure fluid, okay. And then in the zone B, the concentration is going to be exactly same as your initial concentration, that's Cb, and then of course in the sediment you're going to have a higher concentration, right? That's a concentration profile as a function of height. Okay, and then if you wait for long enough time, what will happen is that so your zone B completely disappears, you don't have B anymore. Okay, that means all the particles have settled, they are all at the bottom, and then you have a clear fluid. Okay, this is a typical kind of a behavior that one sees when people do experiment like this. And what people do from this experiment is I can basically track down the interface, right? If I look at the case, the picture in the center, at some point in time I start seeing an interface between A and B, right? There's a clear interface. Okay, there's a interface that basically separates A and B, right? That forms at some instant in time, right? And then of course there's an interface between B and S that could start forming at some instant in time. All people do in such batch settling experiment is that you basically follow the interface position as a function of time. Okay, and what you do is you can basically plot how this is the height of the interface as a function of time. Okay, initially you only, so in the beginning of your experiment what you have is you basically have a clear interface, right? I mean you have you don't have any clear fluid as such. At some point in time, okay, you will start seeing a interface between A and B formed. Typically it starts with some height, and as the time progresses this interface is going to descend, right? It's going to come down. Therefore you're going to see a decrease in the height of the A-B interface as a function of time. Okay, and BS interface, that is the interface between the zone where the concentration is same as the initial concentration and your solid, that is not there initially. There is no initially the height of that interface is 0, right? And as the interface forms, this interface is going to move up, right? Because of which I'm going to see a increase in the height of this BS interface as a function of time. And the point where those two meet is when you have an interface between A and S. Okay, and you could have a case where your A and S could be flat like this. That is going to happen for cases where the solids that are present in the zone S, they are kind of they can support their own weight. Okay, what may happen in some cases is that if there's a compaction that may happen, okay, even after the formation of this A and S interface, what could happen is you could have, so of course S will have some fluid and the particle as well, right? There's a lot of concentration of particles in the bottom, there'll also be some fluid. Okay, now imagine that you may have a case where the particles form some kind of a clusters in the bottom. Okay, now with time you could still evolve. So this AZ may in practice it may reduce slowly, but however if the particles that are present in this S can support its own weight, typically you will see a very constant AS interface, and that's going to remain as a function of time. Okay, so that's a case where you work with some dispersion, and you see the formation of AB interface and AS interface, and finally you will have a AS interface which doesn't evolve anymore with time, right? Yeah. No, this is actually height as a function of time. Okay, what I'm doing is, imagine that I'm taking a photograph of this, right, at different time. Okay, say that the height of the container is say h, for example. Okay, all I do is I start noting. So when say that at some instant in time, this is where the A B interface is. Okay, now what I do is I take this point, okay, and I plot it here. Okay, that's my height of the BA interface, right? So you get the point. So all you're doing is the fact that so the moment you start seeing a clear fluid in your experiment, at that point you have there's a creation of BA interface, right, or AB interface. Okay, all I do is I basically mark the position of that interface, and I'm basically following that as a function of time. Okay, that is this line. Okay, and the moment I see the formation of a BS interface, I start noting down the position and I basically follow the height of that as a function of time, that is basically this line, okay. And the point where they meet is when the AS interface forms, right, okay, and that's your this line. As I said, this could be remaining constant or this could evolve, depends on the kind of particle that you have in the system, okay. If you have, typically if you have a rigid particle, okay, it remains constant. If you have like say a fluid like particle, you know, the emulsions or droplets or something like that, or if you have particles that are squishy, okay, people see some slow evolution, but however that, you know, evolution could be very negligible in the case of hard particles. Yeah. Now, so this is another experiment where what people do is similar to the previous case. Okay, you have zone A, the clear fluid, zone B, where the concentration is same as, you know, the initial concentration. You of course have the sediment at the bottom. There's a zone E where the concentration fluctuations may happen. Okay, what I mean by that is if I look at the concentration plot, right, the concentration in the top zone is exactly, you know, 0. There's no particles there, and B is same as the initial concentration, and you have a zone E where the concentration basically varies as a function of height. Okay, at the top the concentration is as same as, you know, what you have in B. At the bottom the concentration is as same as what you have in S. Okay, however across the height the concentration does change. Okay, and you know, again depending upon, you know, what, you know, so what will happen is your B could completely disappear, and then, you know, you only have an interface between A and E and an interface between E and S, and again you follow that as a function of time. Okay, ultimately you again end up with A and B in the, so A and, sorry, this should be S, right, this should be S, right, that's a sediment at the bottom. Okay, now whether the type 1 sedimentation or the type 2, okay, where you have the formation of this zone where the concentration varies across the height, it typically depends on, you know, what kind of initial solid concentration that you're working with. Okay, typically people have seen that, you know, if you're working with a slurry where the concentrations are lower, typically of the order of, you know, about 20% or less, okay, you see type 1 sedimentation. Okay, however if you go for higher concentration, you know, initially, that's when you see a type 2 sedimentation. The reason why I wanted to talk about such kind of tests is that, you know, you have a lab in the next semester where you're going to look at settling of slurries. You have some experiments where you're going to look at containers which have slurries of different concentration. You're again going to look at, you know, monitoring the interface position as a function of time, and that will, you know, that will help you in terms of obtaining the settling velocities. Okay, we'll talk a little bit about that in the, you know, in the next few minutes or so. Okay, now okay, any questions? So now let's look at so we did this, right, your UP, you know, goes as UT times epsilon to the power of 4.5 is what we did. Okay, but however in general it is typically epsilon to the power of n, right, and I said n depends on what kind of settling that you're working with, right. Now from this what I can do is I can actually define UP yes, which is what is called as a particle settling flux. Okay, UPS is what is called as a particle settling flux, which is basically your UP times 1 minus epsilon, right. I'm basically going back to the superficial, you know, concept, right. So if you want to get the superficial settling velocity, UPS should go as UP into 1 minus epsilon. Therefore I can write this as UT into 1 minus epsilon times epsilon to the power of n. Okay, and I can talk about the dimensional flux, okay, which is UPS divided by UT would go as 1 minus epsilon into epsilon. Any issues? That's okay, right? So I'm basically going back to the superficial velocity concept. Okay, now it turns out that, you know, if I basically plot, you know, this UPS divided by UT, okay, as a function of epsilon, okay, it turns out, it basically goes through a maxima, okay, and then it starts decreasing, and then there's an inflection point here, and then it again goes on decreasing further. You can do that, okay. What you do is you basically take this expression, vary epsilon from 0 to maximum is going to be 1, right? If you do that, okay, you basically get a plot like this. So this, the maxima and the inflection point, I can get it by basically differentiating this equating into 0, and then I can take the double derivative, right? So if I do that, this maxima seems to appear at a concentration where your epsilon goes as n minus 1 divided by n plus 1, sorry, that's going to be n divided by, okay, and this inflection point seems to occur at n minus 1 divided by n plus 1, okay. So this plot is basically the dimensional settling flux, okay, where UPS is your superficial particle velocity, right? That is the velocity which is based on the entire cross sectional area divided by UT, which is the settling velocity under free settling conditions, right? That is UPS divided by UT as a function of epsilon, okay. If I do that, the maxima appears to be at n divided by n plus 1, and your inflection point appears to be n minus 1 divided by n plus 1. If I substitute for n, okay, for the case where we put n is equal to 4.5, right? If you do that, it turns out that this maxima corresponds to 0.177, okay, and this inflection point corresponds to 0.35, epsilon is 0.35, okay. So the reason why I want to do this is because the type of settling that we talked about, okay, whether you have a sedimentation type sedimentation 1 or sedimentation type 2, that basically depends on your initial concentration in the dispersion. Therefore, so these numbers, they basically define some kind of limits where people are going to see a very different kind of settling behavior depending upon the initial concentration that you have in the dispersion, okay. Yeah, is it okay? Any questions? So all that we have done is we took this, the general form of UP goes as UT power epsilon power n. So we took that, okay, and from that we basically obtained what is the superficial settling velocity of the particles, okay, which basically is UP times 1 minus epsilon, right, and I substitute for UP from here, which is UT times epsilon power n. I get this expression. All I have done is I have done the first and the second derivatives, equate that to 0. It gets me access to this and this point. From that I can basically get some values of epsilon. That basically tells you something about the different settling behavior that we saw in type 1, type 2, okay. It basically corresponds to concentrations where the concentration is typically less than 0.177, the type 1, but whereas at a higher concentration you would have a type 2 sedimentation, okay. So that's the reverse, right, because this is the higher concentration, right. Your epsilon is smaller, means your particle concentration is higher, right. So you get type 2 sedimentation in this regime, and whereas in this regime, so basically from here to here you will have a type 1 sedimentation, okay. Whether you have a zone of variable concentration formed or not, okay, it would depend on the concentration that you work with, right. Okay, so now if you go back and take a look at these, let me just go back to, okay, so if you look at typical sedimentation tests, right, it so happens you'll always come across cases where you have a sharp interface, okay, where you have a sharp interface, and that sharp interface separates zones of different particle concentrations, okay. So what I mean by that is, let's take a simple case, okay. I say that I have a case where I start with a certain number of particles here, okay. Say that at some point in time you have a clear interface, that's my interface, okay, Now you have particles of some concentration here, say that the concentration here is C1, okay, that basically is going to be 1 minus epsilon 1, right. I am going to define concentration as in terms of your epsilon is your liquid fraction, 1 minus epsilon 1 will give you the solid fraction. I am going to denote that as C1 in this case. So there is going to be some particles here, say that the particle settling velocity is here is UP1, say that. So you have started with a dispersion of some concentration, and then as I observe the the contents, okay, I see a case where there is a interface formed, that is a clear interface between two regions, where in one region the concentration is C1, in the other region the concentration is C2, which again is 1 minus epsilon 2, okay, and say that your interface is basically moving down with the velocity uint, okay, that is the interface velocity, right. Now if the particle settling velocity is up1 in the above region, and if the particle velocity is up2 in the below region, it turns out that I can think about a simple mass balance, okay. That mass balance typically reads something like this: up1, which is the particle settling velocity in the region where the concentration is C1, okay, minus u interface, okay, that will give me the relative velocity of the particles with respect to the interface, multiplied by the concentration of the particle that you have in the above zone. That should be equal to the up2 minus u interface, which again is the relative velocity of the particles in the bottom zone as a function, related to the interface velocity, multiplied by C2, okay. So all that you are doing is, for the condition is for you to get a clear interface, okay, for you to get a perfectly sharp clear interface, what is the concentration of the particles that reach the interface, okay, from the above should be same as the concentrations, okay, of the particle that leave the interface from the two different zones, okay. This is basically, if you talk in terms of, this is basically the relative velocity, right, times, if you look at this concentration, right, it is effectively a mass balance, okay. Mass flux that is coming down should be same as the mass flux that is going down, okay. Now from this what I can do is I can actually get an expression for uint, okay, that basically goes as up1, so uint goes as up1 C1 minus up2 C2 divided by C1 minus C2, okay. Now if you go back to the cases where I had a region between the clear fluid and the zone of some concentration, okay, I know that one of the concentration is 0, right. I know that one of the concentration is 0, right. Therefore your uint would be proportional to your up1, because if I have cases where I have a zone or an interface which separates a fluid with no particles and a fluid with particles, okay, in such a case one of the concentration is 0. Therefore if you just monitor uint, that is the interface velocity, I can actually directly calculate what is the particle settling velocity, okay. So therefore basically if you have cases where there is a clear, sorry about that, so if you have cases where there is a interface between the clear fluid and a zone where you have particles of some concentration, okay, I can use this formalism that the settling flux, okay, or the mass balance, if I do it, if I get an expression for uint, right, I can actually calculate what is the settling velocity just by monitoring the interface velocities, right. If you look at the case, right, I said that the interface was basically decreasing. All I do is I take this slope, that dh by dt will give me the velocity with which the interface is basically falling. That is exactly same as, I can relate that to the velocity of the particle that are basically settling, okay. Is it okay? Yeah. So yeah, this is only when C2 is 0, okay. But what people do is, now I can actually write this in terms of, but of course if you so when we did this UPS by ut, right, as a function of epsilon than when we did, okay. And epsilon, if I I just use epsilon here, but epsilon would be changing as a function of, depending upon your sedimentation that is occurring, right, your epsilon would be changing all the time, right. Therefore what people do is, we did that the flux plot, right. Then you can actually use I can take 2 points, I can get a tangent, and from the slope there are ways of actually calculating what is your U interface and relating that to interface velocities. Okay, we'll not go into the details of that, but the point that I want to make is that whenever in the experiment that you're going to do in the next semester, you basically follow the interface between the clear fluid and the and the bottom fluid with some particle concentration, and because you are basically measuring U interface, that will be a nice way to back calculate your settling velocities. Okay, this is going to be useful because see, if you are working with, like, say a system where I can observe the particles and look at their position and find their velocities, right. If I have a way of doing that, my job is easy. But if you have cases where you have very fine particles and if the concentration is really large, okay, in such cases, how do I calculate the particle settling velocities? Okay, so the only way of doing that would be basically by monitoring this U interface, and then from that you back calculate what is the settling velocities. Okay, maybe I'll stop here, and I think with this we're going to stop with the concept of so we basically looked at 3 concepts. Okay, settling of single particles, okay, and implications of that in terms of applications, right, and then we looked at settling of aggregates, okay, and then we look at multi-particle systems, right. Okay, that's what we have done so far. Okay, so what I'm going to do in the next class is to look at a case where what you do is you basically have like, say, a pipe, for example, okay, and what we are going to do is I'm going to have a support plate, and then I'm going to fill this pipe with particles, okay, and then we're going to look at how does the fluid flow occurs in cases where I have a container which is filled with particles, and we would like to look at the flow through what are called as packed beds, right. Okay, is what we're going to look at in the next class. Okay, so we'll do that on Friday.